Thank you. Can you hear me and see my slides?
That's perfect. Yes, we can
Perfect.
hear you.
Perfect. So well then, hi from Switzerland. So today I'm going to talk about our new method, physically based shape matching. And I did that together with Miles Mocklin, Nalapong Shentani, and Stefan Jeschke, and we're all from NVIDIA. So let me start with the motivation for our work. A very, very long time ago, in 2005, we had the idea of shape matching based simulation. And this method has been quite popular and has been used over 17 years now. Here you can see the statistics of the citations from Google Scholar. And we now have 750 citations, so you can see people are still using it. And I think the reason why it's so popular is that it's so simple to implement and it's unbreakable. It's very stable. So here I have the video. It has sound, so let me see. Okay, so this was is part of our original submission video of 2005. So as you can see, it's really stable. We could press this duck to a completely flat state. And here is how we do this. So here we have this duck, and what we do is we sample it with particles. And then we simulate these particles without considering elastic forces. So we basically just consider gravity and collision handling. And of course, then you get a very deformed state, and we want to bring it back to the relaxed state. So what we do is we take the rest configuration and map it or match it with the deformed configuration. And for this, we find an optimal rigid transform that minimizes the mass-weighted square distances between the matched positions and the deformed positions. So then once we have that, we simply move the deformed particles towards these matched locations here. For more flexibility, we typically don't just use one group. We split the model into multiple shape matching groups. So here I show you on one slide how to implement this. Now here we have the undeformed shape and the deformed shape, and QCM and PCM are the center of masses. And we specify the locations of the particles relative to the center of masses with QI and PI for the undeformed and the deformed locations. And now once you have that, the optimal translation is just basically a vector from QCM to PCM. Now finding the optimal rotation is a little bit more involved. What we first do is reduce this problem to find the general matrix A. Again, that minimizes the mass-weighted distances between the matched and the current positions of the particles. And fortunately, this problem has a very simple explicit solution. That's what you see here. We have to compute two matrices, a P and a Q matrix, which are basically just the sums, the mass-weighted sums of the outer products of these vectors P and Q. And this guy here only has the Q's, so this can be pre-computed. It's constant during the simulation. When we have computed A, we can now extract the rotational part of A using polar decomposition. And there are many ways to do this. Once we have R, we can then compute these target positions as PCM plus R times the QI here. So, and what's nice about shape matching is it fits perfectly into the position-based dynamics or PBD framework. We can simulate it or use it just as another PBD constraint. So here, very briefly, is the simulation loop of position-based dynamics. At each simulation step, we integrate the particles first, adding gravity and other forces. And then we run through all the constraints. And for each constraint, we go through all the particles that participate in the constraint. We compute update vectors and we add them to the positions of the particles. And as you can see, this what we saw before, the shape matching is has exactly this form. And then at the end, we update the velocities. Now, we actually don't use PBD, we use extended position-based dynamics, or XPBD. There's a very small difference between the two. XPBD is basically PBD plus handling stiffness in a physically correct way. So now, what are the pros and cons of this shape matching idea? One big pro is, of course, it's unbreakable. It's very stable. It's also quite easy to implement. You can simulate easily very stiff materials because the error propagates through entire models, or if you use many shape matching groups, through a shape matching group at once. And it recovers from completely flat states. And another nice property is you don't even need a mesh. You just need a bunch of particles. The disadvantage is it's difficult to tune stiffness, but that's not a really big problem. The really big problem of this method is that there's zero volume conservation. So you don't get bulging. This is a screenshot of another demo from another paper where we simulate this RC car, and we actually use shape matching to simulate this tire here. And what you can see is it's compressed here, but it doesn't bulge. So it doesn't look very realistic. And we actually had quite a few complaints on YouTube from watchers who said, well, this doesn't look right. Why doesn't it bulge? And yeah, the goal of this project is, or was, to fix that problem and to make it more physically correct. So the basic idea we have is we start with continuous material models, like more physically accurate or physically based models. Then we simulate these models using XPBD, and this has been done before by Bender et al. And we also extended the method a little bit. These methods, however, they use Tetrahedra to discretize the models with the finite element method. So these are the basic building blocks, these Tetrahedra. What we wanted to generalize this method so that it works with general particle groups, just as with shape matching. So here's a first result. We simulate each randomized hex cell here as a separate shape matching group. And as you can see here, this is traditional shape matching. You have zero volume conservation. So it doesn't compress in the horizontal direction. And here you see the application of our new method with 3 different material models, the near Hookean and the Hookean, with 2 different Poisson ratios. And we get the shapes, the expected shapes of these models. So in order to explain to you how we do this, I have to give you a 1-page continuum mechanics recap. So in continuum mechanics, a deformation is defined as a continuous map between material or undeformed coordinates x bar and deformed coordinates x. Now, a very important quantity in continuum mechanics is the deformation gradient. And this gradient basically describes the linearization of the transformation at any location in space. And it's the derivative, the partial derivative of the deformed coordinates with respect to the material coordinates. It's a 3x3 matrix. Now, a material model is basically just a function that takes as input this deformation gradient and outputs a scalar potential energy. And here we have an example of a near Hookean material, and there are 2 terms here, a hydrostatic term and a deviatoric term. So as you can see, the inputs are these deformation gradients, and then you have a bunch of parameters as well. Now, once you have the potential energy, you can compute forces as the spatial gradients of this potential energy, and then with the forces you can simulate your material. Now, I also have to give you a brief recap of XPBD, extended position-based dynamics. Here we operate on particles, and we have a bunch of constraints. And each constraint is defined by a constraint function. It's a scalar function that takes as input the positions of the particles that participate in the constraint, and it produces a number that is 0 exactly when the constraint is satisfied. So for any constraint function, we can compute correction vectors for these particles such that the constraint is satisfied, or we can bring the particles closer to a state where the constraint is satisfied. And we do this in general like this. First, we compute a Lagrange multiplier, which is just a scalar. And to compute this, we need to evaluate the constraint function at the current configuration. We also need the gradients of the constraint function with respect to the positions of all the particles. We need their particles' inverse masses. And this is an interesting term. This term basically turns position-based dynamics into XPBD. And here we have alpha, which is the compliance, and compliance is the inverse physical stiffness. This parameter is time step independent. Now, once we have computed lambda, we can compute correction vectors for all the particles participating in the constraint. To do this, we multiply lambda by the inverse mass of the particle times the gradient of the constraint function with respect to that particle. And as you can see, when we can evaluate the constraint function and when we have all the gradients of the constraint function, then we can actually compute these correction vectors for all the particles, and we're basically done. We just have to add them to the positions of the particles. Very simple. Now we have to bring these two worlds together. We have on the one side the continuum mechanics world, and then we have XPBD. So let's have a look again at the near-Hookean potential energy function. We can translate this function, this scalar function, into two constraints. One for the hydrostatic term and one for the deviatoric term. And as you can see here, is that our constraint is 0 exactly when the potential energy is minimized in both cases. So using this constraint drives our model towards a state where the potential energy is minimized, exactly what we expect from a physical simulation. And if we now set the compliances correctly, we can perfectly match the constraint-based formulation with the force-based formulation. But what's cool here is that we actually use the compliances, which are the inverses of the stiffnesses, so we can conceptually simulate infinitely stiff materials, because then these parameters here get infinitely big, and we just get a 0 here. So we just set the compliances of these terms to 0. Now, one problem to go back to XPBD is these constraint functions are functions of the deformation gradient. But in position-based dynamics, we need the constraint functions to be functions of the positions of the particles. So we need a way to compute the gradient, the deformation gradient from the positions of the particles. And this is the point where we have to discretize our continuous model. So we can do this, for instance, with the finite element method and constant strain tetrahedra. And in this case, it's quite simple to compute this unique function f. So let's say we have this undeformed tetrahedron here and the deformed tetrahedron on this side. And now at the qi's here, they are the positions of the undeformed particles relative to particle 0. And the same here, the pi's here are the positions of the particles P1, P2, P3 relative to the particle 0 in the deformed configuration. When we have these vectors, we can easily compute this deformation gradient f by putting these vectors into columns of two matrices P and Q. Again, this one is constant during the simulation, so it can be pre-computed. Now, if we take this definition here and plug it into the earlier formulas that I just showed you, we can actually directly simulate these materials. So what we do is, for a tetrahedron, we take the deformed coordinates here, we compute f, as I just explained, and with that we can immediately compute the constraint function. What we also need is the gradients of the constraint function, and they can be computed pretty easily too. What we need here are these little f's. They're just the column vectors of f. So as you can see, for both terms of the near-Hookean model, we can simply compute these quantities, gives us the possibility to compute the correction vectors for the participating particles of the tetrahedron, and then we can simulate the material. Very simple. Now, if you want to go from these tetrahedral-based discretizations to our case, where we have particle groups, then we need a new way to compute f. So basically what we need is, given an undeformed configuration of a particle set and a deformed configuration, we want to find a linear transformation matrix F. And fortunately, this is exactly what we did in the very beginning for shape matching. So when we computed this matrix A, this is exactly the linear transformation that we need. So we can take the exact same equation as we had before, just plug in these Q's and these P's, and we get the deformation gradient here. Again, we can plug this into the XPBD equations, and we get pretty simple formulas to compute these gradients of the constraint function and the constraint function itself, and then can just use this in the position-based dynamics framework to actually simulate all these different material models. And in the paper, we also give you these equations for the Hookean model. These are the equations for the new Hookean case. So now if you plug that in and run the simulation, this is what we get. On the left-hand side, you see the original shape matching. And when we first saw this, we weren't that happy because these are not small artifacts. This is really bad, unusable, basically. So what's going on here? What's going on is that for 4 points, F is uniquely defined. So if you have two tetrahedra, there's a unique map, linear map from one tetrahedron to the other, if you don't have singular configurations. Now, if you have more than 4 points, then there are motions of particles that do not change F. These are called the zero energy modes. And you have the same problem, for instance, in flip simulations, because there are also many more particles than degrees of freedom of a surrounding cell. And then you can have configurations of particles that do not introduce a divergence term on the grid. So this is a well-known problem, and there are many ways to fix it. One way, by Kugelstadt et al. Yep. I can't hear you. Sorry. I can't hear you. Can you type maybe? Can you hear me? Hello? Can you give me a sign that you hear me?
Okay. Can you hear me now?
Now I can hear you. Could you hear me?
Yes, we can hear you. Unfortunately, Matthias, I have to say to you that your time is already up, and I think you haven't shown already your final result. You know,
oh yeah, okay, sorry, I'm there. Basically, I'm there. So
okay.
I'm already there. So this is the last thing that we had to fix, and we use a filter. You can go to the paper and have a look, but this is really the last problem we had to solve. And here I'm at the results. Okay. So again, this is what I showed you before. And then another result is this twist experiment, where you can see how these different materials behave. Again, the same materials that I showed before. Then here we have very thin sheets, and the user can drag them around. This just shows you how these material simulations are very stiff. And the last one is this fish. So here we cut the surface model into regular cells, and in the inside of the model, these cells are just perfect cubes, but on the outside they're very complex shapes, and we simulate all these cells with shape matching and get this nice behavior for this complex model. So I'm done.
All right, thanks a lot.
Sure.
I'm sorry for the interruption. I didn't see the results section. Who has questions? We have time for one question, at least we will take one question. Do you think to, oh, okay, go ahead.
I can't hear you.
You have two different constellations. But if you go crazy and you have only one element for the entire fish, then what would happen?
Could you hear the question?
Can you repeat it, please?
If you have only one element for the entire fish, what would happen?
I think the duck that you saw in the beginning only had one shape matching group. So it does deform, but you get this problem that you don't have enough degrees of freedom. So you don't get these individual, deformations of the fins here. It looks kind of uniform. You can immediately see that it doesn't have all the degrees of freedom that you need.
Okay. Thanks a lot for your very clear presentation.
Sorry for being too long.
But it's worth it.
Okay, thank you.
Thanks.